All right, what's up guys? In this video, I'm going to pick up some calculus here. It's going to be integration practice video number 11, or example number 11 that we're going to start with. And we're asked to evaluate the definite integral from 0 to 1. We got 2x times cosine to the negative first of x dx. So I actually already posted the solution to this integral on both Instagram and Facebook. So those of you that follow me on those platforms may have already seen the solution to this, but I'm going to quickly go through it one more time just so you can see it in person, or how I got the answer in person. All right, so we're going to apply integration by parts here. The first thing that you need to do is you need to remove the 2, because the 2 is a constant and you always want to factor out constants. So now that leaves us with 2 times the integral from 0 to 1, and on the inside we'll have x times cosine to the negative first of x dx. So keep in mind that cosine to the negative first of x, that's the same thing as arc cosine. Some people write it differently, but it's the same thing. And again, we need to apply integration by parts because we have a product of 2 different functions. So let's do that. So we know that the formula for that is the integral of u dv is equal to uv minus the integral of v du. And we need a u and we need our dv. So those are the things that we need. Now, the selection for u here is obvious. We want u to be cosine to the negative first of x, or arc cosine of x. And the reason for that is because we know that if dv is cosine to the negative first of x, or just arc cosine, remember, to get v, we integrate dv. So we would have to integrate arc cosine. Integrating arc cosine is not hard, but it requires integration by parts. So integrating that, like I said, isn't hard, but it's just a bunch of work that we don't need to do. So the best selection for u in this case would be arc cosine. So just put cosine to the negative first of x, and then dv will be everything else, because obviously x is a lot easier to integrate than arc cosine. So that means that dv is x dx. And so, we go through the normal process and we take our derivative. So remember that the derivative of arc cosine, that's minus 1 over the square root of 1 minus x squared. And it's actually 4 x is in between negative 1 and positive 1. That's not really necessary here, but I was just throwing that out. And then we need v, which is the antiderivative of dv. So that's the antiderivative of x dx, which is x squared over 2. Okay. So I'm going to keep our 2 on the outside here. And I'm going to write everything out just so you can see what happens. So we'll have arc cosine multiplied by x squared over 2, and that'll be minus the integral of x squared over 2 multiplied by negative 1 over the square root of 1 minus x squared, integrated with respect to x, evaluated from 0 to 1. Then we clean it up a little further, so we get 2. And you can kind of clean this side up if any way you like. Remember, multiplication is commutative, so you can kind of clean that side up however way you want to, and be perfectly fine. So if you want to, you can just write it as 1/2 x squared times arc cosine of x minus the integral. And if we simplify on the inside here, it looks like we're going to get negative. It looks like we're going to get negative x squared over 2 multiplied by the square root of 1 minus x squared. And that's going to be integrated with respect to x and evaluated from 0 to 1. Now, the reason why I wrote this side a little better was because, when we actually go through towards when we get to the end, we're going to deal with the constant that we took out. It's a lot easier to expand expressions out or expand out the particular expression that we're going to need to expand out if I have a fraction in the front. So, but again, you can clean it up however you want to. So now the integral that we need to deal with is the integral in negative x squared over 2 multiplied by the square root of 1 minus x squared, integrated with respect to x. That's the integral that we need to deal with next. Okay. So much like the first problem, we extract our constants and take those out. You also want to pull out the negative with it too, because nobody likes negative numbers and they make things far more difficult than they are. So you want to take that out too, along with a 1/2. So now what we really need to integrate is x squared over the square root of 1 minus x squared with respect to x. And we know that's a trig substitution, and it's a sign substitution, because remember, if I have the square root of a squared minus x squared, then x is equal to a sine theta. Now remember, trig substitutions don't have to be under square roots, but in this particular case, it is, and it's a sign substitution. And like I said in my previous videos, if you're struggling with trig substitution, I got plenty of videos on those, so check out my other videos on that. So in this case, since this is a sign substitution, we know here that x is going to be equal to sine theta, and then we need to take the derivative of that, and we get cosine theta d theta. And as I get another sheet here, we'll continue. Okay, so what we do is we go back to what we originally had, and don't forget about the fact that the negative 1/2 was out there. That's what becomes a problem a lot of times for these integrals. You'll forget that you factored out constants. I've done this before, so just kind of keep track of those. So now we got the integral, and we got to substitute in everything. So this is going to be sine theta squared. And you don't want to try to simplify and do everything in one foul swoop. I understand that if you're under a time constraint, then you got to do what you got to do. But you want to take your time, because it's just integrals like this. One little mistake can throw you off. So don't try to rush through things. That's not going to help your situation. Obviously, like I said, if you're in a test or a quiz in a class, you got to do what you got to do. But don't rush. So we're going to take care of that square root first. I always go through all the steps when it comes to trig substitution, because you come to watch my videos to see how things is done. So if I am not showing you guys how to do things, then I'm not helping you. So we got 1 minus sine squared theta. Well, we know we can use a trig identity for that. That's cosine squared theta, or the square root of cosine squared theta. So this becomes the square root of cosine squared theta. And if I take the square root of cosine squared theta, I get cosine theta. So now if I go back to the integral here, I got my negative 1/2 on the outside here. And then I got my integral, and this becomes sine squared theta. Remember, we're multiplying by cosine theta d theta. So cosine theta goes up here, and then down here in our denominator, we substitute in what we have, which was obviously our cosine theta, and that's integrated with respect to theta. And as you clearly see here, the cosines will cancel out, just leaving me with negative 1/2 times the integral sine squared theta. Now we can use a half angle identity, because remember that sine squared theta, that's going to be 1/2 multiplied by 1 minus cosine of 2 theta. So we will replace the integral with that, in addition to pulling out another 1/2. So we got negative 1/2 times a positive 1/2. And then the integral will essentially become the integral of 1 d theta minus the integral of cosine of 2 theta d theta. So this is where we're at after doing the simplification. So we know that this is going to give us negative 1/4. And then this will give us, if we integrate this, remember we get theta here. This is going to be actually 1/2 sine of 2 theta, but we do have a minus sign there. So we'll take note of that factor. So this would be theta minus 1/2 sine of 2 theta. And this is where we're at. We'll go ahead and expand everything out. So we'll end up with negative 1/4 theta It's going to be plus 1 over 4 sine of 2 theta. Okay, I have to expand everything out. Now remember that sine of 2 theta, that's just 2 sine theta times cosine theta. So now we make some changes there. And so essentially we got now negative 1 over 4 theta plus 1 over 4 times 2 sine theta times cosine theta. So if you've gotten that far, then you're on the right track. Okay, so we go back to the substitution. So x was sine theta, remember? So that means that sine theta is equal to x over 1. And if we think about the Pythagorean theorem, SOHCAHTOA, if you want to think of it like that, SOHCAHTOA, SOHCAHTOA, we know that sine is going to be, or sine theta I should say, is going to be opposite over hypotenuse. So we'll note that. We also know that cosine theta is going to be adjacent over hypotenuse. So the moral of the story is we know what the opposite side for the triangle would be x. We know that the hypotenuse would be 1. So the only side that we're missing is the adjacent side, and we need that because we took sine of 2 theta and turned it into 2 sine theta times cosine theta. So to find the ratio for cosine theta, we need the adjacent side, which we don't have right now. So that's why the Pythagorean theorem gets applied in this case to find the missing side. So we'll continue to go with this. So as we continue, I'll put it right there. That way I can just stack it up over here. So we need the adjacent side. Okay. So this is where we use our a squared plus b squared equals c squared. That's where this becomes very handy. And we already know what the opposite side is. We already know what the hypotenuse is. So that means that we get x squared plus b, b squared, we're missing the adjacent side, and then 1 squared is 1, so we leave that alone. We subtract x squared from the both sides, and then we'll just get b squared is equal to 1 minus x squared. Taking the square root of both sides, we get b is equal to the square root of 1 minus x squared. Okay. So this would be our adjacent side of the triangle. And as I mentioned in the video that I did the other day on trig substitution, sketching out the triangle is not required, but it is sometimes helpful. So we'll just go ahead and draw our right triangle, and we'll stick in all of the information that we need to stick in. So we already knew what the opposite side was. We already knew what the hypotenuse was. Remember, hypotenuse is the longest side of the triangle. It's the triangle that's directly across from the right angle. And we now have the adjacent side, which was the square root of 1 minus x squared. Okay. So you don't got to write that, or you don't got to draw it, but again, it's just sometimes helpful. Now we can find the cosine ratio that we needed, which was adjacent over hypotenuse. So that's the square root of 1 minus x squared, basically all over 1. So that's the ratio for cosine theta. And then one more time, sine theta is x over 1. Okay. Let's also note the fact that theta is going to be equal to arc sine of x. So if we go back, we had negative 1 over 4. We changed theta to arc sine, so this becomes arc sine, or sine to the negative first. And then this would be plus 1/2. And the reason why it's going to be plus 1/2, because if we go back to what we had here and we do the simplification, 1 over 4 times 2, well, you can cancel out a 2. And so now this just leaves us with 1/2 multiplied by x over 1, multiplied by the square root of 1 minus x squared, all over 1. And then when we simplify here, we get negative 1 over 4 arc sine. And this will be plus the square root of x times the square root of 1 minus x squared all over 2. So this is what we get when we evaluate the inner integral here, where we started out with the by parts. And remember where we evaluated that? Remember, that's what we were doing, believe it or not. And that's what makes this integral, I wouldn't say it's super complicated, but you got to be very careful, because we did the integration by parts at the front end, and it's just seemed like we went off on a tangent and we're just on some other problem, but we're actually still on the same problem. And that's what makes this one, like I said, I don't think hard, but you need to be very careful with it. So now if we go back to the original integration by parts that we had, and by the way, technically speaking, we should add a plus c. If we were evaluating it as an indefinite integral, we would technically add a plus c, even though this is a definite integral, so the c necessarily isn't required. But if you want to be technical with it, then you could put it there. But you don't need to put it there in this case because it's a definite integral, but you can at the beginning. Okay, so let's go back to the integration by parts that we had. So remember, the 2 was on the outside, if you remember. And then we had 1/2 x squared arc cosine. And then it was plus 1 over 4 arc sine plus x times the square root of 1 minus x squared all over 2. And now it's from 0 to 1. All right, so next step is, if you would like to go ahead and distribute in the constant to, okay, I mean, you don't have to. If you want to plug in the limits first and then multiply by the constant that was pulled out earlier, that's perfectly fine too. So it doesn't matter which way you do it, but we need to stick in a 1 and then stick in a 0. So it's pretty obvious to see what we get when we stick in 0, but let's just go through it and stick in a 1 just to kind of go through the whole thing. So we got 1/2 multiplied by 1 squared arc cosine of 1 plus 1 over 4 arc sine of 1 plus 1 times the square root of 1 minus, you stick in your 1, so it'd be 1 minus 1 squared all over 2. And then you would essentially do the same thing with the 0. So then if you plugged in the 0, it would be, it's actually going to be, not going to worry about the 2 right now, we're just going to worry about 7 in the limits. And so if we stuck everything in, this is what it would be. Now remember, we're subtracting the result of this from the result of what we get when we stick in the 0. So that's going to be plus 1 over 4 arc sine of 0 plus 0 multiplied by the square root of 1 minus x squared. And then that's going to be, I'm sorry, 0 squared all over 2, and then we would subtract. Okay, and that's how it should be set up. And now if we finish it out, let's get another sheet here to finish this up. All right, and you can even use your calculator as well to validate your answers. So let me just quickly show you. Now, remember that cosine of 0 is 1, but arc cosine of 1 is going to be 0. So we know that. And same thing for if we have our arc sine, that's 1.57. And so we would have 1 over 4 times that. And then we'd have the square root of 0, so that'd be 0. And then we multiply that by 2, so that'll essentially give me pi over 8 if I did substitute it in the 1. So we'll get 2 times pi over 8. Now sticking in the 0 is obvious. We're going to get 0 here, and we can even prove it because remember that 0 squared is 0. So if I'm multiplying anything over here, it doesn't matter. I'm multiplying that by 0, that by 0. Same thing over here. Arc sine of 0, just to prove it to you. Oops, sorry. Is also 0. So with that being said, we know that basically anything over here is also 0 because 0 times whatever that is 0. Again, arc sine of 0 is 0. So 1/4 times that is also 0. So the obvious answer for the substituting in the 0 is 0. So it would be 2 times 8 pi minus 0, which is 2 times, not 8 pi, but 2 times pi over 8, excuse me. 2 times pi over 8, which we know it just reduces down to pi over 4. And that would actually be the answer. So our final answer for this integral here is pi over 4. And that's how you do it. So it was the integral from 0 to 1. And it was 2x arc cosine of x integrated with respect to x. And our answer here is pi over 4. And that's how you solve it. So I had posted some solutions to the problem earlier on social media because I was teaching someone earlier, helping them with integration. And we went through one that was similar to this in the example that I was helping him with. And so basically what I did was I went into my calc textbook and tried to find one that was similar to the one. His wasn't exactly the same, but it looked a little something like this. I think it was 4x times arc sine, or it's something similar to this. So that's why I went to the book and got one that looks a little similar, and I thought I'd do it and we could do it on video for integration practice, example number 11. So that's why you may have already seen the answer to this one, but this is how you do it by hand. And so hopefully that makes sense. And if you guys got any questions about how I got the solution, let me know. We can go over it. All right, I will see y'all next time.